serves as an associate professor in the Electrical and Electronics Engineering Department at Marathanesius College of Engineering, Gopinadhan. Dr. Sija's academic credentials reflect her dedication and expertise in the field. She recently earned her PhD in Power Electronics from the prestigious National Institute of Technology, Calicut in 2023. She holds an M.Tech in Power Electronics from Kerala University, completed in 2005. She began her journey in engineering with B.Tech in Electrical and Electronics Engineering from MG University in 2003. Her areas of interest including high-gain DC to DC converters underline her focus on cutting-edge advancements in power electronics, a field critical to the future of renewable energy and efficient energy systems. Today, Dr. Sija Gopinadhan will guide us through an engaging topic, Introduction to High-gain DC to DC converters and its control techniques. The session promises to provide valuable insights into the design, operation and control of DC to DC converters, which are essential components in modern energy systems, enabling high-efficiency power conversion for a variety of applications. Ladies and gentlemen, please join me in welcoming Dr. Sija Gopinadhan with a warm round of applause in the stage.
Thank you. To start with my presentation, this is my agenda for my presentation. Brief introduction to high-gain DC-DC converters. That means only basic classification of this high-gain DC-DC converter and its controller DC. So I'll start with a small story. I think you are aware of the story, War of Currents. Third War of Currents. It's actually a war between AC and DC transmission systems. It's initially we have a DC system of transmission actually that is done by this Edison. Edison actually running a company on DC lighting system, and after that Tesla come up with the idea of AC, but what happens is Edison is actually running this company on a patent basis and he is investing a lot in that one. So he is not ready to accept the concept of AC. But Tesla says that since the invention of this transformer will benefit for the transmission of AC system at lower cost, but Edison is not ready to accept that. And for that, what Edison done is some public awareness camp is conducted so that AC is dangerous to human beings as well as animals, like that he demonstrated. Finally what happens is this Westinghouse is ready to take this invention, AC transmission system, and in his company he started that AC transmission system. Finally AC wins over DC. That's the previous system. It has happened in the 19th century. But after that, what happens is now the system is again developing and renewable energy sources are coming into the action. Nowadays, we are commonly using AC systems, but in near future, maybe we are migrated towards the DC system also, because majority of the renewable energy sources are producing their output in DC. So maybe we can migrate to this, again we can migrate back to DC system of transmission. So DC is very important in this point of view, and also in electric vehicle, this DC means the battery which is working as a DC source. So DC-DC converters plays a major role in the case of an electric vehicle also. So different types of power electronic converters are there. Each one, all these are having applications in the domain of electric vehicle technology. You know that this power generation based on non-conventional energy sources are increasing day by day, and we can use this source for integrating this EV into our existing system. But the problem in these sources are it is highly intermittent nature, and so we need some kind of proper integration, and these are having distinct voltage current characteristics. So some kind of integration interface device is required to integrate a DC-DC converter or high gain boost converter came into our mind, what happens is the gain of a normal boost converter is 1 by 1 minus d. And we know that we cannot increase the duty ratio in an infinite time. There is limitations due to its parasitic effect. So what happens is only we can increase the duty ratio up to 0.8 so that we can get a gain of only up to 5 volt. So gain of 5. That means if we are giving a 48 volt input, we can produce 48 into 5 by using this normal boost converters. And we know that if you want to produce a 3-phase AC, 400 volt 3-phase AC, minimum 650 volt DC is required in the front end. So we need to have a 650 volt input in the front end, and our input is only 48 volt. So we need a high gain converter in between this. We can introduce this high gain converter in different way. Either we can use a transformer or we can use 2 or more boost converters in cascaded manner. Anyway, there are the different ways to improve the gain of the system. But when you are using more number of circuit means that will cause more losses in the system and it reduces the efficiency of the system. So for that we need this high gain. There comes the need for this high gain DC-DC converters. And these high gain converters are having some mention that later some non-minimum phase characteristics. So in order to work this in a proper manner, we need to design some kind of controller also. So mainly high gain DC-DC converters. I will mention about the various type of high gain DC-DC converters and the techniques which is used for obtaining high gain. That is the first part of my presentation. So the high gain converters we can classify in different ways. First way is a non-isolated and isolated converter. Second way means it can be unidirectional or bidirectional converter. It can be a voltage fed or current fed converter. It's hard switched and source switched converter, and last classification is non-minimum phase and minimum phase converters. First classification is non-isolated or isolated converters. The name non-isolated or isolated means there is no non-isolated converter means there is no isolation, there is no electrical separation between the input and output. That is called a non-isolated converter. That can be of two types. One which is having common ground. Here you can see. Here you can see that this is a common for this ground is common for both input and output. So this is called a non-isolated converter with the common ground. This kind of normal boost converter is an example of a non-isolated converter with the common ground. So this ground is common for both input and output. Some applications specifically replace this kind of common ground. And second classification means one there is no isolation between input and output, but there is no common ground between input and output. 3-level boost converter is an example of a converter with no common ground. Here you can see that one diode is here. So due to the presence of that diode, there is no direct means sometimes there is no connection between the two grounds, input ground and output ground. Now, if you need isolation, specifically if you need grid interfacing and all, you need these isolated converters. So isolation can be provided directly into the converter so that this input part is isolated from the output part, or it can be a cascaded structure. Means you can use a non-isolated DC-DC converter in the front end, and after that you can use this isolated converters. The isolation can be provided by means of transformers or by means of coupled inductor. Then next classification is unidirectional or bidirectional converter. Unidirectional converter means power flow is from only one direction. So that means here the power flow is only from A to B. This kind of converter is called a unidirectional converter. Example is our normal boost converter is an example of a unidirectional converter. Bidirectional means the power flow can be in both directions, input to output and output to input. The same boost converter, if you replace with the diode is replaced with the switch, we call it as a synchronous boost converter. It's an example of a bidirectional boost converter. Then these two are non-isolated converters. Now coming to isolated converters, there also unidirectional and bidirectional is there. So normal full bridge DC-DC converter is an example of a unidirectional isolated converter. Then bidirectional isolated converter is also there. So this is an example of a bidirectional DC-DC converter. This popularly known as the dual active rich or dark converter. Actually, now research are going on to this. Many research works are going in this area of dual active rich DC-DC converters. Mainly its control techniques. That means here the power flow is controlled by means of phase shift between the two ends of the two sides of the transformer. So that phase shift can be achieved by different ways. So that control method is actually prominent area for research. The next classification is the voltage fed or current fed converter. That means if the input voltage remains constant, means it will not change with the output, we can call it as a voltage fed converter. And current fed converter means we are keeping the input current almost constant. For that, usually we will connect an input stage, we will have an inductor in series with the source. So this kind of current source converters are mainly used for applications such as photovoltaics and fuel cell, which needs a constant input current. So such applications we can use current fed DC-DC converters. Then another classification is hard switched and soft switched converters. Hard switched converter means every converter is having one or more than one switches. So the turning on and turning off of the switches will actually cause some losses in the system. So during the turn on or turn off process, if any one quantity, voltage or current, if we are able to make that zero, means the losses that are happening during the turn on or turn off can be reduced. So the hard switched means will not be zero. So there is some voltage or some current present during the turn on and turn off process. But whereas in source switched converters, either of these quantities become zero. So we call it as zero current switching or zero voltage switching. Is it CS or is it DS? So different types of elements are used for obtaining this zero switching or zero current switching or zero voltage switching, like resonant time converters. This can be in the form of series LC circuit. Resonant circuit is formed using L and C circuit. So it can be series, parallel, or the combination of series, parallel. Different types of combinations are there. These are called, generally we can call it as the resonant time networks. It is actually inserted in the converter so that we will have it is in series or parallel with the switch switch, and we can use that converter for the we can use this network for the zero crossing or voltage or zero current or zero voltage switching. Then another method is we can use a quasi-resonant switch sets. Here we are using a auxiliary switch for the auxiliary switch is used for making the ZCS or ZDS. Then another method is active snapper cells are there. The next classification is non-minimum phase and minimum phase converters. Non-minimum phase converter means, so control system, you know that we can say system is stable only when all of its poles are on the left half of S plane. If any one of the pole is on the right half of S plane, means the system becomes unstable. But when the system is having its zeros on the right half of S plane, then we will call it as a non-minimum phase system. Open loop, there is no problem with this non-minimum phase system because all of its poles are on the left half and the system is in a stable condition. But when we come to closed loop, what happens is, we know that when we load the root blockers, we know that actually we are plotting like this, the pole is actually moving towards the zero side. So what happens is, when you design a converter, if we are not properly designing the converter, means there is a chance for the pole to move to the right half of S plane where the zero is present. So what happens is the system will then become unstable. And most of the high-gain DC-DC converters are having minimum one pole in the right half of S plane. So we can reduce this effect of this right half plane zeros by reducing the inductor value, but it does not eliminate the right half plane zeros, but it can shift the poles far away from the imaginary axis. So when it is shifted far away from the imaginary axis, means what happens is the effect of this non-minimum phase is reduced. Then operating in DCM also allows for very stable dynamics without any RSP0. And nowadays, new type of boost converters are also introduced or come into the literature, like KY converters, which uses additional active switches to eliminate the right half side half plane zeros. So all these are coming to the interest when we are going to design a closed loop controller for the system. So many of the system which requires closed loop controller. So when we design closed loop controller for this system, we need to consider the RSP zeros and we need to design the controller values accordingly. So I have covered the main classification of this DC-DC converters. Now coming to the different techniques which is used for obtaining the high gain DC-DC values. You can classify it as switched capacitor method, switched inductor method, then a combination of switched inductor and switched capacitor, then voltage shift technique is there, voltage multiplier technique is there. That are the different methods to obtain high gain DC-DC converter. High gain in the converter. First method is called switched capacitor or charge pump based converters. Here what we are doing is we have a capacitor C1 here and another capacitor C2 here. So when the switch S1 is turned on, this capacitor C1 charges with the input voltage, and when switch S1 open and S2 close, what happens is the charge that is stored in the capacitor C1 is discharged to C2. So this way we will call it as a charge pump circuit. The charge from the C1 is discharged to C2 in the next step. So that is the basic charge pump circuit, but here the output voltage is same as the input voltage. The same circuit we can make it as a switched capacitor circuit in this way. What happens here is when the switch is in 1-1 position, the capacitor stores the charge and its voltage become equal to V in. And when switch comes in 2-2 position, what happens is that this input is come in series with the capacitor and these two. That means this input and capacitor C1 both deliver power to C2. So the output voltage of the voltage of C2 becomes 2 times V1. That is what the switched capacitor consists. This is same only here. Here the advantage is we can introduce any number of stages in between this. Then different types of other switched capacitor techniques are there. Ladder type structure is there. Then Fibonacci series like that one will produce the output voltage in Fibonacci series. So the advantage with this circuit is we are using only capacitors or switches and diodes for this circuit. So the circuit is cheap and lightweight. It's having smaller size and higher density, higher power density. It can be easily integrated into an existing system, and its dynamic response is very fast. But what happens is we know that whenever we are at the initial stage, we know that if the capacitor is not charged, what happens when we connect it to the DC source, high inrush current is flowing into the circuit. So that is a major problem with the switched capacitor circuit. So the inrush current is very high at the starting stage. Then the ESR of the capacitor here sometimes creates some problem, and the output voltage regulation is also having some difficulty with this kind of configuration. And these are mainly used in energy harvesting applications, automotive and vehicular applications, and high gain DC-DC applications. The next one is the voltage multiplier circuit. So these are there are two types of voltage multiplier circuit. One which we can introduce between the input and output stage. Usually so this is the three circuit mainly used as an output between input and output of a DC-DC converter. So what happens is if you have a DC-DC converter which is having an output voltage of, for example, 10 volt, when you introduce this into the circuit, what happens is the gain is increased by usually by it's a multiplying 2 times multiplication will happen. So you get a 20 volt output if you insert this kind of multiplier cells in this one. The main theory is actually the capacitors are charged in parallel and it discharges in series. So charged in parallel means suppose that it is charging with a voltage of V in, both the capacitor will charges with a voltage of V in, but when the time of discharging these two beings, two capacitors are come in series, so that two being is discharged to the load. Two types of control, these two are looking similar, but the application consists, this is used when our main switch is in a parallel with the circuit. So if we have a main switch in a parallel circuit, then we can use this kind of configuration. And if our circuit is series connected, if our switch is series connected, then we can go for this kind of configuration. And here the active switch is connected in series with the multiplier cell. You can see here. So in both these cases, what we are doing is we usually place the switch on the input side, so that the voltage stress on the input side, the voltage is less compared to the output side. So what happens if the voltage stress on the switch is less, if we introduce the rectifier after the multiplier after the switch. Here also we can introduce this after the switch. Only difference is this is used when we have this in our circuit, we have the switch parallel with this. Then only it will work. And in this case, the switch is in series with this circuit. So that one time when the switch is on time, the capacitor is discharged. Both cases when the switch is on time, the capacitor will discharge, and when switch off time, the capacitor will charge through this diode. And next one, we can have voltage multiplier rectifiers are there. It can rectify AC to DC, or it can change the pulsating DC. Two types of voltage multipliers are there, half wave and full wave structure are there. This Gopinadhan voltage doubler is very famous. Then different types of configurations are there. Here the difference is this full wave and half wave difference means full wave will rectify only one half cycle, so that we will get it, and the output we will get 2 times beam, but what happens only in the positive half cycle. Whereas in this full wave circuit, it rectifies the both sides, so that we will have output in the positive and negative half cycle, and that too 2 times the input voltage. So these are having very high voltage. By using this kind of circuit, we can increase the voltage, and this is cell-based structure. Cell-based structure means we can introduce this in any kind of DC-DC converters. By adding this converter, means this cell in between this existing DC-DC converters, we can increase the gain of the system and can be integrated into various structures. But since we are using this cell is actually placed in the between input and output, so the components of the cells are actually stressed with more voltages. So high voltage stress on the component is there, and if you want to have high voltage rating and high power application, we need to connect several such cells, so that will reduce the efficiency of the system. These are mainly used in medical, military and physics, plasma accelerator. This kind of voltage multiplier cells are used for obtaining high voltages. The next technique is called the switched inductor techniques and voltage lift technique. Switched inductor means there is passive switched inductor. Passive switched inductor means there is no active switches present, only diodes are present here. So what happens is the same theory behind switched capacitor. That means these are charged in parallel and discharged in series. So these two, when the switch is maybe in on or off condition, one condition if this two capacitor inductor will charges, and when any one of the when the switch is in off condition, this may discharge in series. So this is using only diode. That's why it is called the passive switched inductor. You don't want to turn on and turn off it. They automatically turn on and turn off. The same can be implemented by using active switched inductor cells. Instead of using these diodes, we can use switches. Instead of we can use switches. And this is called a voltage lift, active switched cell with a voltage lift technique. So here we are having additional current capacitor is placed. So that what happens is this capacitor will also get charged during one stage of the system, and that charge voltage can be further used for discharging to the load. So along with these two inductors, that capacitor voltage is also used for charging the output capacitor. So that will increase the gain, or will get a voltage lift. So if this is having a voltage of DC, the output voltage is shifted that much DC times. Two capacitors are present, so 2 times DC is the output voltage. So this is called voltage switched hybrid ASL cell. So in the previous case, we have an inductor here, another inductor here, and two active switches. This is called active switched inductor. And if you replace this inductor with this cell, so these inductors we can replace with this cell. This is called a hybrid active switched inductor network. So this is having high boost stability and it is used in many converters. The drawback is it needs more passive components like inductor